Welcome to Gradient Daily. Today, we're analyzing a May 2025 paper by Abhishek Joshi and 14 researchers titled Procedural Generation of Articulated Simulation-Ready Assets. The engineering objective driving this research is specific: deploying general-purpose robots into complex, unstructured human environments, like homes and factories. Computer vision algorithms have largely solved the problem of recognizing static objects, but when a robot attempts to manipulate an object with dynamic moving parts, like a latch or a hinge, the control models frequently fail. The physical friction of interconnected mechanical parts creates unpredictable feedback that rigid training models cannot process. To bypass this limitation, the researchers developed Infinigen-Articulated. It is a software toolkit designed to procedurally generate a limitless supply of simulation-ready 3D assets, specifically for training robotic manipulation policies. Training a robot to handle complex, moving parts in a highly controlled virtual simulation is the only way to bypass physical damage and slow iteration cycles of real-world training. Think of this engineering problem like training an airline pilot. You rely on a flight simulator because crashing a physical plane during trial and error training is unacceptable. However, that flight simulator provides zero value if its underlying physics engine fails to accurately compute the aerodynamic drag of severe weather conditions. If the math is wrong, the training does not transfer. In robotics, the equivalent of severe weather is joint kinematics. A robot simulator must mathematically replicate the exact physical resistance of pulling open heavy doors, sliding heavy wooden drawers, or operating spring-loaded hand tools. If the simulated physical assets are not exact mathematical representations of their real-world counterparts, the AI policies trained on them will inherently fail when deployed on a physical robot. To understand the solution, we have to define the problem domain. An articulated object is defined as any physical object composed of multiple rigid parts connected by moving joints. Generating a static 3D object is like rendering a solid garden statue, a unified mesh. An articulated object is an action figure, requiring mathematical nodes for joints. When it raises its arm, its center of mass dynamically shifts, requiring real-time simulator recalculations. Because the physical structure is constantly reconfiguring itself, the collision boundaries that the robot sensors rely on to map its environment are simultaneously expanding and contracting. The Infinigen-Articulated toolkit tackles this geometric complexity by providing procedural generators for 18 distinct categories of articulated objects. These generators output standard storage cabinets, complex hand tools, and even scissors, each governed by different kinematic rules. Relying on researchers to manually sculpt and assign joint limits for thousands of variations in CAD software is an immense waste of labor. Instead, algorithmic generation allows engineers to instantly spawn vast, diverse datasets with effectively zero marginal cost per simulated asset. Training control policies purely on static 3D data is obsolete. Dynamic, multi-joint object interaction is the new mandatory baseline for any viable robotic manipulation system. The toolkit achieves this volume by integrating custom high-level code utilities directly into Blender, an open-source 3D creation suite. The system uses a simple numeric seed value as a genetic code. Inputting a single number spawns a completely unique geometric variation of an object type. For example, inputting seed A might generate a heavy oak cabinet featuring 2 wide doors attached with stiff brass hinges. Inputting seed B forces the algorithm to produce a completely different physical profile, a wider, lightweight cabinet with sliding doors running on high-friction tracks. This procedural capability drives a critical training technique called domain randomization. By constantly altering the visual textures, weights, and physical dimensions of the training assets, the system prevents the neural network from simply memorizing the exact dimensions of a single training cabinet. The procedural engine effectively creates an infinite, constantly evolving curriculum. It forces the AI to learn generalized manipulation strategies that work on any cabinet, rather than overfitting to one specific shape. However, generating thousands of visually perfect 3D models in Blender solves only half the problem. If a simulated robot tries to grab a purely visual mesh, its gripper will clip right through it like a hologram. It is the difference between baking a CGI cake for a movie prop and baking a real one. To actually pick up the object, the robot simulator needs strict data regarding its density and weight distribution. The researchers built a specialized export pipeline that calculates and preserves these exact physical parameters. As the asset leaves Blender, the pipeline attaches concrete numeric values for total mass, surface friction coefficients, and precise angular limits for every joint. This export pipeline is the critical bridge in the toolkit. It translates raw visual geometry into strict, actionable mathematics that advanced robotic simulators like Modular or IsaacSim require to run accurately. Once these procedurally generated assets are exported with their physics profiles intact, they are bundled into structured datasets for experimental training. First, researchers use them for movable object segmentation. This trains computer vision algorithms to analyze a complex object and computationally isolate the specific parts that are capable of moving. Next, the assets are deployed in reinforcement learning, or RL, environments. Here, an AI agent learns to physically interact with the dynamic objects through a relentless process of trial and error. The agent's behavior is driven by a mathematical loss function, calculating a reward or penalty based on manipulation success. Within that equation, specific variables track joint states, evaluating the agent's ability to align moving parts with target angles. The dataset is also used for imitation learning. Instead of trial and error, expert human manipulation data is cloned and mapped directly onto the simulated models, teaching the AI the optimal paths for interaction. By supplying endless, physics-ready variations, Infinigen-Articulated provides a completely penalty-free playground for engineers to test and refine multiple AI training methodologies simultaneously. The ultimate test of this system is zero-shot sim-to-real transfer. This is the process of taking a policy trained exclusively in a virtual simulation and deploying it on a physical robot to interact with a physical object it has never encountered before. The paper demonstrates a major experimental success. Physical robots equipped with policies trained on these generated assets successfully manipulated entirely novel, real-world articulated objects on their very first attempt. The sheer volume and extreme domain randomization of the simulated training data successfully shielded the AI. It did not fail or lock up when faced with real-world lighting glare or unexpected surface textures. This bar chart compares the sim-to-real success rates. Older models trained on limited, static datasets exhibit high failure rates in dynamic manipulation, while the models trained on the Infinigen-Articulated datasets show a massive increase in successful physical execution. The simulation parameters were so rigorously generated and varied that to the AI's neural network, physical realities simply felt like another procedural variation it had already solved. The immense scale of this project, coupled with its open-source integration directly into Blender, offers a permanent structural fix for the chronic data scarcity holding back robotic manipulation research. However, we must critically evaluate the physical assumptions of the toolkit. The procedural generation relies heavily on rigid body physics. It is unclear if the current export models adequately account for soft body deformations, such as a plastic latch bending under pressure before it unclips. Furthermore, there are questions regarding the tribology models. A static friction coefficient assigned during export may not truly capture the micro-level wear and tear or the variable resistance of a real-world hinge that hasn't been oiled in 5 years. The logical next step for this research is to test these highly dynamic, procedural assets against complex, multi-fingered robotic hands, rather than standard two-pronged parallel grippers. To summarize today's breakdown, first, the toolkit automates the creation of 18 distinct categories of articulated assets. Second, its export pipeline perfectly pairs visual geometry with strict physical parameters. And third, these datasets enable robust zero-shot transfer from simulation directly to physical robots. Thank you for joining us on Gradient Daily. Subscribe and turn on notifications, and check back tomorrow as we dissect the next critical breakthrough in AI and robotics.